Einstein is famous for his equation E equals mc squared, but do you know that he actually won his Nobel Prize for an equally important equation, E equals hf? This equation is famous for relating energy and mass via a constant, the speed of light. And this equation is quite similar. It relates the energy of light to its color via another fundamental constant called Planck's constant. Now, this equation kicked off the field of quantum mechanics, and this constant is the constant that determines the size of most quantum effects. So as you can imagine, it's super tiny. But in this video, we're going to do a simplified version of the experiment that won Einstein his Nobel Prize, and in the course of it, we're going to measure this Planck's constant, all using some LEDs. This video is sponsored by KiwiCo, by the way. More on them later. But I do want to clarify one thing first. So Einstein didn't do the experiment himself. He got the Nobel Prize for explaining an experiment that other people had done. And of course, that experiment didn't actually involve LEDs because these things hadn't been invented yet. Instead, it involved shining light on various types of metals. It did something very unexpected. See, this is what they would have expected from the classical theory of light.
Light has energy in it, and the brighter the light, the more energy it's got. And the way that energy manifests for a wave is in its amplitude. The bigger it is, the more energy it has. In fact, the amount of energy in light is proportional to the amplitude squared. So for the energy of the light, it doesn't matter at all what the wavelength is, just how big the peaks are. The wavelength just determines the color, but the amplitude is the energy. The thing light wants to do with all of that energy is donate it to a charged particle, like this electron here. When the electron is all alone, it can receive any amount of light. The more it gets, the faster it flies off. But it's a little bit more complicated when the electron is bound up in a metal. The reason the electron is trapped in the metal in the first place is because it doesn't have enough energy to fly away. For each metal, there's a fixed amount of energy that the electron would need to break free. When light shines on it, that's the electron's opportunity for escape. The electron doesn't mind what color it is. As long as there's enough energy in the light to break it out, the electron can escape. The extra energy then might just go into how fast it flies off. Only this story is what you would expect from classical electromagnetic theory, and it turns out not to be right.
When you actually do this experiment, you find that color does matter. When the experimenter shines low-frequency light on the metal, no electrons get released. This is true even if you shine the light very brightly, meaning it has plenty of energy to give. The electrons in the metal just don't seem interested in it. On the other hand, if you have high-frequency light, the electron does take it. So what's going on? Both types of light have the same energy. Why does the electron ignore it in one case, but absorb it in the other? Einstein had a really neat solution to this. He said, what if the total amount of energy just depends on amplitude? So both of these have the same amount of total energy. But whenever light like this wants to give some of its energy to, let's say, this electron, it's not just the total energy that matters. There's also one other factor that you have to take into account, and that is that the energy from this light is broken up into chunks. These chunks of energy are called photons. As you can see, the red light, which has low frequency, also has very low energy photons, whereas the blue light, which has high frequency, has high energy photons. So that's what E equals hf is actually referring to. E is the energy per photon, and F is the frequency of the light, so in other words, the color. And we can see that if the frequency is low, that the energy is going to be small, whereas if the frequency is high, then the energy is going to be quite big. When light interacts with an electron, instead of giving that electron all of the energy, it gives the electron just one photon's worth. So let's say we have a color of light that has really big photons. And so if that one photon has enough energy to free the electron will take that freedom, plus any surplus energy will just go into its kinetic energy. On the other hand, we might have another color of light shining with a lot less energy per photon. Now the electron won't get enough energy to escape from one photon. So it doesn't take any energy at all,
even though many photons may be raining down on it, none of them are good enough. So the genius of Einstein isn't that he came up with this equation himself. In fact, Planck had come up with a very similar equation, which is why this constant is named after Planck and not Einstein. But when Planck wrote this equation down to solve another problem, which was called blackbody radiation, he just thought it was a cute mathematical fact, but he never thought that it corresponded to anything physical. He knew that light is made out of waves, and there is no quantization of light. Whereas Einstein took this equation seriously. He said that, okay, light might be a wave, but there is a thing that's quantized, and that is the amount of energy it's allowed to transfer to another object. That comes in chunks. And that kind of quantization is what kicked off the field of quantum mechanics. It's where quantum mechanics even gets its name. So this was an incredibly important result. I wanted to do a version of this experiment that was totally foolproof, and that's when I came across this LED version of the experiment. We're essentially going to do Einstein's experiment in reverse now. So Einstein's experiment shone light on some metal, and then that made the electrons inside of that metal flow, which you can measure inside of a circuit. But here we're going to do the opposite. We're going to make electrons flow, and those electrons are going to make light. So let's say this is our circuit for the LED, and we have our battery with some fixed number of volts. That means that an electron that goes through this battery has picked up 2 electron volts. So electron volts is just a crazy unit of energy, but it's very convenient because it lets you go straight from the voltage of the battery to the energy that the electron will have. So by the time it goes around this circuit and to the LED, it will give that 2 electron volts to the LED and then go back. But we want to figure out what the minimum amount of energy is. 2 electron volts is more than required for this LED to turn on. Each one of these LEDs only gives out a very specific color of light. So in other words, the LED determines the frequency of the light coming out. And this LED needs a certain minimum amount of energy to make 1 photon worth. And that minimum amount of energy is given by the equation E equals hf. If this electron has enough to meet that bar, then this LED can make some photons. If the electron doesn't have enough to meet that bar, then the LED ignores it and doesn't light up. So if we can get to the point where this electron has just enough energy to light up this LED, then we've figured out what that minimum amount of energy is. And so in other words, we've measured what E equals hf is, but we already know what F is because that's determined by the color of this LED. So we can figure out what H is. So what do? We actually want to decrease the electron's energy on the path. So we could just add a resistor. The resistor is going to use up a bunch of the electron's energy. So it's going to come out the other side with much less. Depending on the size of the resistor, the electron's energy might have gone down to, let's say, just 1 electron volt. And so now, when it goes to this LED, it only has 1 electron volt worth of energy to give. And so we can test if that is enough to turn on the LED or not. We can keep testing this with either bigger or smaller resistors, and eventually we're going to find some energy, which we'll call E, which is the exact minimum amount of energy to turn this LED on. But because it's the exact minimum amount, we know that it must be equal to hf, where f is given by the frequency of the red light, and h we can now measure. So that's the experiment we're going to do. We're going to do that though using these adorable mini breadboards from this kit from KiwiCo. As I rig up this circuit, I want to tell you a little story. So when I was 12, I did this unit about electricity in school, and for the project we had to make a circuit or something. And I made this little board game where there were a bunch of switches and you have to click things, and I don't even know if it was fun to play, but it was so fun to make and I learnt so much. And I remember at the end of that experience that I told everyone I want to be an electrician. because I didn't really know that there was such a thing as being a physicist. But what's kind of crazy is that like all these years later, I kind of fulfilled my childhood dream. And it all started with a very simple little experiment like this, a toy that I helped co-create. And that's what I really love about KiwiCo. Every month, KiwiCo sends your kids a crate that they can use to make a project, and then they can play with that project for the rest of the month. I know how valuable that kind of exploration was for me, and so I'm really excited for kids in the future to be able to do these kind of experiments for themselves and learn things by doing. For engaging projects that spark a passion for STEM, I think you'll really love KiwiCo. Click the link in the description or use my code LOOKINGGLASS for 50% off your first kit at kiwico.com/lookingglass. Okay, so look at what I made. This little breadboard is actually the exact same circuit as the one we drew here. All that's happening is we have the battery pack, and this here is the resistor. And as you can see, it works. But this is a very small resistor right now, and so the energy of the electron is pretty close to the 2 electron volts that it would have gotten from the battery. We want a stronger resistor in here so that eventually there's not enough energy to turn on the LED. If we can just keep trying different resistors until we get to the exact point where this LED no longer turns on, then we'd be done. But that is a lot of work. And so instead, I bought this special little thing. This is called a variable resistor. So if I turn this little knob, then it turns up the resistance from 0 all the way to 1 million. This is 0 resistance, and then that is higher resistance. So we want to find the exact point where there's not enough energy to make light. I think that might be it. Let's see. Nah, there's still a tiny, tiny little flicker of light. Turn the resistance up a bit more. I'd say that's off. Okay, so now we're going to use a multimeter to figure out how much energy this is. This exact point where there's no longer enough energy to make light, which should roughly be equal to HF. The way we're going to do it is we're going to measure the voltage across the LED. But that's okay because there's a very simple way to convert the voltage here to the energy the electron has. All we have to do is whatever voltage this is, let's say it's like 1.5 volts, then the energy of the electron is equal to 1.5 electron volts. So as long as we measure the voltage, we know how much energy the electron lost as it moved across this LED. So let us indeed measure that voltage. Oh, nice. 1.5, 1.54. The frequency of red LEDs like this is typically around 4.7 times 10 to the 14 hertz. And so dividing the top number by the bottom number would give us Planck's constant. But it'll only give us one estimate of Planck's constant, right? We have all these different LED colors, so why don't we just do the same experiment for all of them, and then we'll see how good our estimate of Planck's constant is. Okay, so the green LED is on. Let's turn it off. Okay, that looked like it was off. Why is this happening? Okay, so at this low level of resistance, this green light is still on. It's very faint, but you can just about see that. It's still not off. I didn't get it. That doesn't make sense. Okay, let's see. Why is it 1.9? It shouldn't be 1.9. I'm definitely doing something wrong. I don't understand this. I feel like this is going the opposite way than it should. Okay, so it's a different day. In fact, it's several days later, because when I was trying to do this experiment, I kept getting a very unexpected result. I thought this experiment was foolproof, but apparently not for me. You see, what happened was every time I turned down the voltage, I'd still be able to see just a tiny little bit of light, and it never kind of turned off at some point. Well, I looked into it, and it turns out that that is actually fairly easy to explain, and I will tell you about that.
But after I answered that question for myself, I had more and more questions about LEDs and PN junctions, and now I've learned much more than I thought there was to know. So I think that's going to have to be a separate video about LEDs. But for now, let's just go back to the picture that we were using because that is more or less correct. What we said before was that this electron goes around this circuit with a certain amount of energy provided from the battery, and it's able to dump that energy into light at the LED and then go back less energetic. If the electron has an energy of HF, then yeah, it will definitely have enough energy to make some red light. But what happens when the electron's actually picked up less than that amount of energy? Then surely there's no possible way for the electron to go through and make light. But this is where I was going wrong. Actually, there is. You see, there is the energy that the electron gets from the battery, but there's always a small amount of thermal energy in any system, and so this electron just has a certain amount of that. That may be enough with the small amount of energy it gets with the battery to make light. And so sometimes the electron will get enough energy from the thermal energy plus the energy from this battery to make light. Even if there's no battery whatsoever, it's possible for this to happen. In fact, apparently LEDs emit about 20 photons per second, even when they're not attached to anything else. So this is why, no matter how much I turned down the energy, there was always a little bit of light, and our eyes are insanely sensitive to light. So even when it was very low, I was still able to discern it. But it is still true though that if the energy drop across this LED is equal to HF or greater, that there is going to be much more light being produced. So what we're looking for is the voltage where you transition from a background amount of light to a very significant amount of light. And that voltage at that transition is what solves this equation. So let's do the experiment. Okay, so somewhere in there, you can see that the transition doesn't happen at exactly one point. There is like a little bit of leeway in that transition. So I'm not 100% sure where to put it. So maybe what I'll do is I'll record sort of a low number and a high number. Like here's the high number. Okay, I reckon that's the low. 1.8 to 1.86. Okay, I'll go ahead and do that for all the other ones. 1.85. 0.9. All right, so I've done it for all of these, except for the blue one because this battery was a bit too weak to like fully turn on this LED. Now, what I would do if I was a good experimental scientist is that I'd find out the frequencies of all of these LEDs, and then I would plot these data points on a graph, and from the gradient, you would be able to figure out what Planck's constant is. And that would give you by far the best results. But I'm not gonna do it. I'm not gonna do it because, well, mostly because I'm lazy, and it would involve a little bit of work. So let me explain. Figuring out the exact frequency of this light is a little bit tedious, and so instead I'm going to cheat. I'm going to use the fact that, at least for this red LED, I know exactly what the frequency is, and from that I'll be able to use this threshold voltage and figure out at least one estimate of Planck's constant. I have no idea how accurate that's going to be, but let's find out. All right, so that's the frequency. The threshold voltage is somewhere in there. Let's rearrange to get H. We're hoping that this is going to be approximately equal to 6.63 times 10 to the negative 34 meters squared kilograms per second. Let's see. This is an incredibly tiny number. I would be happy just to like roughly get into the same order of magnitude. So let's put in first our low threshold value and see what we get for H. Wolfram alpha is really good for these kind of calculations because it like deals with the units for you. So let's see. Okay, so that's crazy. The number we were going for is this, and what we actually got was 6.73 times 10 to the negative 34. Basically, very, very accurate. That's crazy. Okay, let me just try the high threshold number to see if that was better or worse. So that one would have given us this, which, yeah, is a little bit worse, but still very, very close to the real thing. Okay, so it turns out that you can measure this fundamental quantum constant that is absolutely tiny, and is what sets the scale for quantum mechanics using a single LED fairly accurately. That's crazy. This was a really fun experiment, and it went a lot better than my experiments usually go, so thanks for joining. And by the way, if you are interested in KiwiCo, the link is in the description. Thanks very much. Bye.